First, we start with Dr. Arthur Mutter. Dr. Arthur Mutter started mechatronics at the University of Stuttgart, 2012. He finished his PhD in the area of communication networks. The topic of his PhD thesis was the memory architecture of high-speed routers with more than 100 gigabit per port. Since 2010, Dr. Mutter works at Robert Bosch GmbH in the area of hardware IP development. He was significantly involved in the development and standardization of KNFD. Currently, Dr. Mutter is responsible for the standardization of KNXL, and since 2018, he is chairperson of the special interest group KNXL at KNN Automation, which specifies the KNXL data link layer, physical layer, and higher layers. As I've already said, today he is presenting compatibility of KNXL and KNFD. So we are very happy to have you with us, Arthur. So please, the stage is yours.
Rainer, thank you very much. Thank you for the introduction. As you may have observed, in the agenda on the website, this webinar is titled Interoperability. Now we talk about compatibility. Why did he change the title? And I was myself confused. And therefore, in the last weeks when I prepared the slides, I just checked in the internet, what is the definition of compatibility and interoperability? Because I wanted to find a really right term. And here's what I found. So I found on this website here that compatibility means two things able to exist or occur together without problems or conflict. So two things can exist together without problems or conflict. And interoperability is defined as the characteristics of a product or a system to work with other products or systems without any restriction. And from this, I said, okay, so KNXL and KNFD are like two languages, right? And two languages cannot be interoperable because Chinese and English is just not interoperable. So, but it's compatible. So they can exist both. A Chinese guy and an English guy can stay next to each other and they can coexist, right? They don't disturb each other. They know the other one is talking and so on. So I thought compatibility is the perfect term here. And therefore, I will use in my presentation the term compatibility all over. Nevertheless, there are also other terms you could use. For example, coexistence is also possible, or tolerance. However, compatibility fits the best, and therefore I will go with compatibility. So this is just to explain the terms. Now, the question is, what will we see in this presentation now? And as you know, there are microcontrollers out there with KNFD that implement KNFD. And soon, hopefully in very few years, we will have microcontrollers which implement KNXL. On the other side, we already have high-speed CAN transceivers, KNFD transceivers. Now, newly on the market, the so-called signal improvement capability transceivers, so the so-called SiC transceivers. They can even do a higher speed, so they have better edge symmetry. And soon we will also see so-called CAN SiC XL transceivers, which are even faster. And now the target of this webinar is to answer the question, how can I build now from these components nodes? And how can I build from these nodes systems or networks? And this is the question. So how can I build a mixed KNFD KNXL network? Are there restrictions or not? And if there are restrictions, which ones? What do I need to care for? And also, when I have a KNXL node, in which network can I use it? Are there some restrictions, or is all the stuff software configurable or not? And since this topic is not that simple, it's not that complex, but also not trivial. Therefore, we will need another 40 minutes to make really sure everybody understands the relations. Here you see the OZ layer model. And you see, we start at the bottom from layer 1, the physical layer, to the data link layer, network, transport, and so on, up to the application layer. And the CAN-FD and the CAN-XL protocol are located here on the data link layer. And the transceivers that we know, the SIG XL transceiver, SIG FD, and high-speed transceiver, high-speed CAN transceiver, are located on the physical layer. Here on the network and transport layer and application layer, there are many more protocols related to CAN-FD and soon also to CAN-XL. However, in this webinar, we do not talk about them. So the focus of this webinar is really only layers 1 and 2 and their compatibility. So this is important to know. We will only talk about these 2 layers, which is totally sufficient for this webinar. So now we know the wording, the exact scope of the webinar. Now we can head on to the agenda. So the agenda looks pretty simple. First, we will take a look on layer 1, on the physical layer, understand what's going on there. Then we'll take a look on the OSI layer 2, the data link layer, understand what's going on there. And then we will learn some things. And then we will put all we learned together in a resulting compatibility overview. And after that, we will see some examples to understand the whole thing and to, And afterwards, for sure, you will have a lot of opportunity to ask questions, because I target to take 45 minutes and then we'll have roughly 15 minutes to answer questions. So if you have any questions, please write it to the chat and then we will be able to answer it later. Okay, so let's start with the physical layer. Compatibility on the physical layer. So as you know, there are a lot of CAN transceivers out there. I consider only the relevant ones, and the relevant from my point of view are the high-speed CAN transceiver. This is the one that is typically used with classical CAN. And this one is limited to 1 megabit per second. Then we have the CAN-FD transceivers. These are limited typically in real networks, let's say it that way, to 2 megabit. According to the ISO standard, they can even do 5 megabit, but this is only on the paper. So in real networks, they are limited to 2 megabits typically. And then we have the CAN-SIG transceivers, so signal improvement capability. And these are limited to roughly 8 megabit. And then we have the new transceivers, the CAN-SIG XL transceivers. You see, this is an extension of the SIG transceiver by some new functionality, XL. And these are roughly limited to 15 megabits, roughly. Nobody knows exactly the border up to now because, the transceivers are currently built and first samples are available, but we will need to find out where the exact border is. And the point is, this bitrate is now in the data phase achieved. So you see, I wrote here fast mode. So we will take a deeper look at this transceiver, what's going on here. Here you see the transceiver modes. You see the first 3 transceivers have just 1 mode. They are stupid, simple, 2 pins, done. However, this new transceiver has now 2 modes, the SIG mode and the fast mode. We'll see soon what this means. And to make description now simpler and the pictures a little bit nicer, I will use now abbreviations for these transceivers. So high speed, HS for high speed, FD, SIG, and XL for the individual transceiver. Otherwise, it won't fit to the figure. Now, when we think about the node, which transceivers can we use in which node is the question now. And a CAN-FD node supports all transceivers. That's a good message. However, you see, you need to use it in this first mode, the SIG XL transceiver. You're not allowed to switch the mode. And a CAN-XL node, which will be built soon, so a microcontroller with CAN-XL capability, will also be able to use all transceivers. So this is a good message. For any of the nodes, I can just use any of the transceivers. So there's no hard linking. And that's a good message. And that's maybe the takeaway from this slide. We have different transceivers, but we can use all transceivers for all node types. Now, since the CAN-SIG XL transceiver is new, let's have a look at it, how this works. Here, I have a list of two modes. One is the SIG mode, and this is the default mode of the CAN SIG XL transceiver. And this is identical to this. This can generate two bus levels, the dominant and the recessive. And this is identical to the CAN SIG transceiver and identical to the high-speed CAN transceiver, the two levels, the dominant and recessive. So 100% compatibility, everything is fine. However, to achieve the really extreme bit rates that we want to achieve with CAN XL, there was no chance to do it with dominant and recessive, because a transceiver only has under control the dominant and the recessive only partly. And therefore, there was no chance to go beyond 8 megabit. And therefore, we said, okay, we need a new mode, and then we will do better. So this transceiver has a second mode, the so-called fast mode. And a transmitting node does now a push-pull in this fast mode. So it sends zeros and ones, not anymore dominant and recessive. So zeros and ones, both bus states are driven. And the receiver will stay high ohmic for sure, and will adjust his thresholds because he needs to receive now these new levels correctly. And what is important to know now here, in this fast mode, since we have a push-pull, so zeros and ones, we do not support error frames anymore. So this was the price. Having this second mode with very high speed, then we lose error frames. You will understand the consequences in a few slides. And somebody needs now to tell the transceiver to switch back and forth between these two modes to operate smoothly. And the one who does it is the CAN XL protocol controller. So the one who sends the frame tells the transceiver, hey, now switch to this mode, switch back, and so on. And here you see a MAC frame that is transmitted by such a CAN XL protocol controller. So this is the view on layer 2. And you see, at the beginning, we have the arbitration field with the identifier. Then the data phase follows. These are the short bits that are transmitted with a high bit rate. And then at the end, you see again the arbitration phase. And you see the two blue fields here in the frame. The ADS, this means arbitration to data switch. And you see the DAS field, the data to arbitration switch. And during these two fields, we do two things. The one is we switch the bit rate from slow to fast. And also we tell the transceiver, hey, please switch your mode. And these two fields here have a few bits, and they add a lot of tolerance because we switch the bitrate ratio really from 500 kilobit, for example, to 10 megabit or even to 15 megabit. So it's a very big bitrate ratio. And this is how it works. During this ADS field, we start a signaling to the physical layer. And then he knows, oh, I need to switch from the SIG mode to the fast mode. And then he will stay in fast mode. And then at the end of the frame, we will tell him, oh, hey, stop signaling, go back to SIG mode, because we need to send the acknowledge and so on. And then he will go back. And for sure, this will be slightly different for the receiver and the transmitter. But basically, this is the way how it works. So this is the basis. Now let's have a look on even more details of this CAN SIG XL transceiver. And here you see the different differential voltage levels and the different thresholds that such a transceiver has. This figure is copied from the specification we currently do at SIA. However, I colored a lot of things here, so it's not the original figure, it's a modified one. And what you see here is on the left, during the SIG mode, the transceiver can drive or provide, it doesn't drive it actively, the recessive level or the recessive bus state and the dominant bus state. And you see dominant bus state means 2 volt differential, roughly. And you see the threshold is here. So it's 900 millivolt. When you're above, it's a dominant. When you're below, it's a recessive, a 1. So 0, 1. However, then we switch the level or the mode of the transceiver to the fast mode. And here things look different. You see, we have here the so-called level 0, which is a positive differential voltage of 1 volt. And you see the minus 1 volt, which corresponds to the level 1. So this is a logical one here. and this is a logical 0. And you see, we use here a threshold at 0 volt, and that means the two thresholds are different. So the consequence is now that the high-speed CAN FD or SIG transceiver, oh no, differently. A high-speed CAN and CAN FD and the SIG transceiver only have the left mode, the SIG mode or the dominant and recessive bus states. So old transceivers only support dominant recessive differential levels and the according thresholds. The consequence is they cannot detect voltage levels used in the fast mode reliably. And that means a level 0, here, this one, if this is not that good with 1 volt, if it drops a little bit, because there are also tolerances, then you see it can drop a little bit below this threshold. That means a level 0 of the fast mode may be detected as recessive by an old transceiver, because it doesn't see it, it's below the radar. And therefore, when you start mixing these two transceivers, an old one and a new one, then the old transceiver may see, oh, the bus is idle, I can start transmitting, but no, he can't. Somebody's communicating. And therefore, what we learned from this slide, legacy, high-speed CAN, FD, and SIG transceivers are incompatible to fast mode of a CAN SIG XL transceiver. You see, the incompatibility is only regarding to the fast mode. So if I take this new transceiver and operate it only in the SIG mode, everything is fine. When I switch it to the fast mode, it is not compatible anymore. So this is the takeaway from this slide. Now let's have a look on what's going on layer 2, so the data link layer. And the CAN protocol variants that we know, so the languages that we know, are the following. We have the classical CAN, known since 30 years, CAN FD, known since roughly 8 years, and then we have CAN XL, born 2 years ago. And you see, just to visualize it somehow, classical CAN can transmit up to 8 bytes, CAN FD up to 64, and CAN XL up to 2048. And there's even a mistake here in the slide, like I see now. CAN XL cannot send 0 bytes. Here it should be a 1. So CAN XL has 1 up to 2048 bytes. And now, again, it's important to know that the CAN FD node, which you can buy today, supports both classical CAN and CAN FD. So it implements both. And a CAN XL node that you will be able to buy soon will support classical CAN, CAN FD, and CAN XL simultaneously. So it can do all things at the same time. So you will be able to send one frame in classical CAN, then another in CAN FD, and another in CAN XL format back to back. So this is an important takeaway. The nodes always support the older variants also. Okay, now we know about the CAN protocol variants. Now the question is, let's have a look on the details of CAN FD. And during the development of CAN FD, or during the specification and standardization, roughly 8 years ago, we had in mind that there may be a successor of CAN FD, which is now CAN XL, and therefore we built in something, this red bit, to be compatible to it. So there is this red bit, and when an old CAN FD node sees this red bit as a 0, then it knows it's a CAN FD frame and everything is fine. However, when a CAN FD node sees this red bit as a 1, as a receiver, then the CAN FD node enters the so-called bus integration state. This is a passive wait state. And the CAN FD node finishes now this bus integration state when the CAN XL frame ends. So when he will see the 11 recessive bits. And when we now compare this to languages, when CAN FD is English, the English language, and CAN XL is Chinese, then these two languages have nothing to do with each other. However, the one who can speak English understands, oh, there is some other language, I don't understand it, but I just wait until this guy finished his sentence and then I start my sentence. So this is a comparison which fits really well from my point of view. Okay, so that means a CanFD node tolerates or ignores CanXL frames. He cannot understand them, but he just tolerates and ignores them. So this is the way how we achieve compatibility. We just close our eyes in a CanFD node. Okay, now let's have a look at CanXL. In CanXL, we now need to distinguish between two operating modes. And the good thing is that these modes are configurable in software during runtime. So you can change the mode at any time. And what is also very important, all the nodes in one bus or in one network must have configured the same mode, right? Mixing of modes is not allowed. And these are the two modes now. The one is error signaling enabled, and the other is error signaling disabled. So what means this? So error signaling enabled means that this node will do error signaling with error flags. And this is the typical behavior as CAN does it since ever. And it's identical to how it is done in CanFD and also identical to how it is done in CAN, in classical CAN. So this is the usual CAN behavior. And if we have this mode enabled, so error signaling enabled, then we are fully compatible to CanFD. And because CanFD also uses error signaling, right? This is the reason both use error signaling, they are fully compatible. And the frames that we can send now on the bus are CanXL frames, CanFD frames, and classical CAN frames. We can do all. Now, we learned before when we took a look at the transceivers that the SIG CanXL transceiver cannot support error frames. So we needed to implement the possibility to switch the error frames off. And this is the possibility. This is the one mode, error signaling disabled. When I disable it, I will be able to use the new transceivers. However, I will not have error flags anymore. So error signaling disabled means that errors are not signaled. So when a receiver sees an error, he does not tell the other nodes. He will just reintegrate and wait for the end of the current frame and then will be ready for reception or transmission again. And for sure, a transmitting node will behave a little bit different. He will just not care for any errors. A transmitting node, when he started the frame, then he will finish the frame. So he will not check for errors. He will just say what he wanted to say. And due to this different behavior here, now we get incompatible to CanFD. So this is the reason. We need to switch off error signaling to be able to support the new transceivers. And since we switched off error signaling, we get incompatible to CanFD. And as consequence, for sure, CanXL are the only frames that we can send here. We are not allowed, it's even forbidden by the standard to send here CanFD or classical CAN frames. So only CanXL frames can be sent here. So the takeaway is CanXL is compatible to CanFD when error signaling is enabled. This is the takeaway. Okay, now let's have a deeper look on a CanXL node. So we had a CanXL protocol now. Now we take a look at the node. And such a node, as we saw at the beginning, supports classical CAN, CanFD, and CanXL at the same time. And the consequence of that is that we have also 3 bitrate configurations available in a CanXL node. The one is for the arbitration phase. This is called the nominal bitrate, which is limited to 1 megabit. Then for CanFD, we also additionally have the data phase. For this, we configure the so-called FD data bitrate. And the FD data bitrate has to be larger or equal to the arbitration, to the nominal bitrate. So it's not allowed to be smaller. And since we also support CanXL, we can also configure the CanXL. For the CanXL data phase, we can configure the CanXL data bitrate. And the CanXL data bitrate has a small constraint. It has to be at least twice the nominal bitrate. So when we configure 500 kilobit for the nominal bitrate, we need to use at least 1 megabit for the data bitrate here. And the reason is we use less stuff bits in CAN-XL, and therefore the distance between two stuff bits gets bigger. And to still enable error frames to work, therefore we needed to restrict the bitrate ratio. So you always need to use twice, at least twice the nominal bitrate in the database. Okay. Except or additionally to these bitrate configurations that we have in such a node, we also have some configuration parameters. The one you already know, it's the error signaling, which can be disabled and enabled. However, we have a second parameter that is very important. This is the transceiver mode switching. This can also be enabled and disabled. So the node can tell the microcontroller to signal to the transceiver some mode switching or not. So we can tell him what to do. And now we get the truth table out of these two configuration parameters. And here on the right side, you see what's the outcome. This is now not so easy to understand because we did not see the examples yet. But maybe if you look at these slides later, after this presentation, then it will be much easier to understand. So I anyway go quickly through it, but you will understand the things soon. So when I have the transceiver mode switching disabled, so we do not talk to the transceiver regarding mode switch. And when I have error signaling disabled, this means I use an old transceiver and I do not send error frames. The consequence is I only can use CAN-XL frames, and this corresponds to a fire and forget communication. So fire and forget is I just send a frame and don't care if it's somebody received it or not. And for sure, I'm limited to bit rates up to 8 megabit because I cannot switch the transceiver mode. It's disabled. The default operating mode that people will use at the beginning will be for sure this one, where the transceiver mode switching is disabled and the error signaling is enabled. So the absolutely standard CAN operation mode. Here I'm fully compatible, can send all types of frames. However, I will be limited to 8 megabits. But for the first step, when I use CAN-XL, maybe this is a good choice. Then I have the mode where I enable transceiver mode switching and disable error signaling. So I can use the new transceivers and disable error signaling. That means I only can send CAN-XL frames, again, fire and forget style. But since I switch to transceiver mode, I can reach 12 and even more megabit due to the new transceiver. And this will be the high speed use case and the corresponding configuration. And finally, we still can enable both error signaling and transceiver mode switching. However, this is invalid, this is forbidden because the transceiver doesn't support it. You can still do it, so nobody hinders you. You just can do it, but you will see it will not work. As long as there is no error, it will work, but as soon as there's the first error, your system will misbehave. Okay, so far to the node. Now let's see the conclusion for compatibility on layer 2. The conclusion is that a CAN-XL and the CAN-XL protocol and the CAN-FD protocol are compatible, so they can live next to each other when a CAN-XL node has error signaling enabled. Then I'm able to build such a network. I'm able to build a mixed CAN-FD CAN-XL network. That means I have two types of nodes in the network, the legacy CAN-FD nodes and CAN-XL nodes. And since you know that we even have 3-bit timing configurations in the CAN-XL node, we can even configure different bit rates for CAN-FD and CAN-XL. The CAN-FD node anyway cannot understand the frame, so he also doesn't care if we use a different bit rate in CAN-XL. And the other thing we learn is that when the CAN-XL protocol and the CAN-FD protocol are incompatible, so they are not allowed to live in the same network when the CAN-XL node has error signaling disabled. That means when I disable error signaling, I'm only allowed to do CAN-XL communication with CAN-XL frames. However, in this configuration, I can build pure CAN-XL networks with high speed. So this is the advantage that I get. And I reach 12, maybe even 15 or even more megabits. So this is the takeaway now from layer 2. Now we learn stuff from layer 1, from layer 2. Now we take all this knowledge and put it together in one figure. Now we look on layer 1 plus 2. What does this mean? Because at the end we have nodes and that we want to place in a network. So on this slide, we will take a look on the layer 1 and the layer 2 successively. So let's start with the layer 1. We know there are FD and high-speed CAN transceivers. There are SIG transceivers, and there are these SIG-XL transceivers. And you see, I have drawn here a big box. And the big box is because these transceivers can be used without mode switch and with mode switch. And it depends on software, on the software configuration in which mode they are used, right? So it's the same transceiver used in 2 modes. And here is the bitrate. I just colored it from yellow to orange that these transceivers support. And now with green lines, I will connect those boxes which are compatible. And you see FD transceivers, SIG transceivers, and SIG-XL transceivers without mode switch, which are used without mode switch, are all compatible because they have the dominant and recessive levels. They can understand each other. Everything is fine. Now let's have a look. And you see there is no line to here. There's just no green line because this guy here used 2 modes with different threshold and voltage levels, and it's just not compatible to the others. Now let's have a look at layer 2. On layer 2, we have 2 things. CAN-FD and classical CAN. I put the 2 guys into the same box. I could have used also a separate box for classical CAN, but the slide was too small, so we just limit ourselves to one box with CAN-FD and classical CAN staying together there. And we have also CAN-XL. And you see, like I said, there is a software configuration where I can say error signaling on or off, which means enabled and disabled. And this is, again, software configuration. And as long as I have error signaling on, these 2 guys, FD and XL, are compatible. And the compatibility means CAN-FD ignores the XL frames, so he just doesn't care. And he waits until the frame is over. And you see again, no line from here on the right side to the left, because error signaling off means incompatible. Okay, now let's start connecting these 2 layers. And you see, CAN-FD protocol can work with all types of transceivers. For sure, it cannot do the mode switch. It doesn't have the capability, but it can work with all of these transceivers. A CAN-XL node with error signaling on also can work with all of these transceivers, no problem. And when I switch off error signaling, this node can still work with all of the transceivers. This use case doesn't make so much sense, but you can just do it if you want. And now, if I want to go to higher bit rates, I now can start switching the mode of the transceiver, and then I can draw here a line. So error signaling off is compatible to SIG-XL transceivers with mode switch. And this is at the end the map where you can check what is possible or not. And since this map looks a little bit complex, we can start mark areas here in there. And you see there are, I call them islands. And you see there is the left island. And when I'm inside the left island, then I'm fully compatible. So there is a full compatibility of CAN-FD and CAN-XL if I limit myself to 5 to 8 megabits. So I have to care about nothing here on the left. I just can combine anything with anything, it will work. And the limit is 8 megabit. If I want to achieve a higher bitrate above 8 megabit, then I get to this island 2. And this means to achieve that, I need to switch my transceiver mode. To be allowed to do that, I need to switch off error signaling. And by this, I get incompatible on both, on layer 2 and layer 1. And this is the right island. So for high speed, I get incompatible. This is the takeaway. And for speed or bit rates up to 8 megabit, I'm fully compatible. Anything is combinable with everything. And this is the takeaway, these two islands from this slide. Now, we also learned or saw at the beginning that a CAN-XL node will support all three flavors of CAN. So CAN-FD, classical CAN, CAN-XL, and for sure with both modes, error signaling on and off. That means a new node will be able to support everything. But what does this mean? This means for the usage, a big flexibility, because when you build a CAN-XL node with a CAN SIG-XL transceiver, you can just use it as a CAN-XL ECU with super speed, right? You can use it at 12 megabit. However, just by software configuration, you can use this node, you can use this node as a CAN-XL ECU, as a regular one. So without super speed, right? You just turn on error signaling, which is even the default mode. And then it got a CAN-XL ECU. And you see this CAN-XL ECU can live in a CAN-FD network. So you can start build mixed networks here. And you can even further downgrade this ECU. And you say, okay, by software configuration, I even disable CAN-XL. And then this node will be able to communicate only with CAN-XL, with CAN-FD and classical CAN frames. And this is then a regular CAN-FD ECU, even if it has the new transceiver, because the new transceiver is operated in SIG mode, so everything is fine. So the takeaway from this slide is we have extreme flexibility with a new CAN-XL ECU. And this is the message here, yes. Very flexible usage of a CAN-XL ECU. Okay, now let's move on to the examples. Now we learned a lot, and I will show you now a lot of examples and to make it more understandable. So before I start with the examples, I want to introduce the building blocks from which I built my examples. And such a block is a node. It consists of the protocol part. So this is the newest protocol version it supports. And if it supports CAN-XL, like we heard before, it also supports CAN-FD and classical CAN also. So it always supports the older versions. And the small box here is the transceiver. And you see we have SIG-XL transceivers, SIG and FD, and also high-speed CAN transceivers. So we will have at the end high-speed CAN-XL nodes and CAN-XL nodes with just the SIG transceiver, which is already available today, the SIG transceiver. Then we will have, in the examples, CAN-FD nodes, but new ones, because the SIG transceivers are only available since very soon, so since months. And then we will have here also legacy CAN-FD nodes. These are CAN-FD nodes, they're already in the field, and they have CAN-FD transceivers, so the 2 or 5 megabit CAN-FD transceivers. And so this is a legacy node, an old one. And we'll also have the legacy classical CAN nodes, which are really old CAN nodes. Okay, now let's start with the first examples. Example 1. I can build mixed CAN-FD and CAN-XL networks. What does this mean? You see here I mixed CAN-FD, a legacy CAN-FD node, with a legacy CAN-FD node with CAN-XL nodes that even have the SIG CAN-XL transceiver. And what are the settings that I need to make? For example, I can configure the arbitration phased bitrate to 500 kilobit, because this is the typical bitrate that can be easily supported by an FD node, because he has a poor transceiver, let's say it that way. Then in the FD data phase, the CAN-FD nodes are limited to 2 megabit. They can not do more in big topologies. In small, they could do more, but this is now a bigger topology, let's say 2 megabit. And since the CAN-XL nodes use the SIG-XL transceiver, so they have better transceivers. So they can have a better signal quality on the same topology because they have signal improvement capability built in. Therefore, on the same network, these transceivers can support 5 megabit or even more. However, these transceivers are only operated in SIG mode, right? We do not start switching the mode of the transceiver. And what I also need to do is the CAN-XL nodes need to have the error signaling enabled, because CAN-FD nodes also have error signaling enabled. They cannot switch it off. And that means this is one example that absolutely works. 2 megabit FD, 5 megabit CAN-XL, and they all live in the same network. Everything moves, works smoothly. I tried this several times in the lab, and it really works. It's not just on the paper. Another example is the following: the pure CAN-XL network. Here, I can use, let's assume it's the same topology, right? Here I can use in the arbitration phase a higher bitrate, because I have now very, very good transceivers that operate in the 6 mode in the arbitration phase, and it's just waste when I only operate them at 500 kilobit. They can do more. However, there's also a limit, and I just have chosen here as example 650 kilobit. So we do not need to stick with SIG transceivers to 500. We can go further. So the arbitration phase 650, and in the XL data phase I just choose 12 megabit because this is a bigger topology, and 12 should work for sure here. And you see, error signaling is disabled, and therefore I'm not allowed to use CAN-FD nodes here. Independent if they are new or old, we don't care. We are not allowed to use them here. So these are maybe the most prominent examples, and I think these networks we will find soon out there in the world. Now the following examples are maybe more exotic and maybe not that popular than outside. So what you can also do here is you can do a pure CAN-FD network, a pure CAN-FD network with 2 megabits. What does this mean? This means I use again XL and FD nodes. However, I operate the XL nodes in FD mode, so I just switch off the CAN-XL feature. This is again a software configuration bit. And that means I just configure 500 kilobit in the arbitration phase, 2 megabit FD data phase, error signaling stays enabled, and then I have just a kind of downgraded XL nodes to CAN-FD, and I can build my CAN-FD networks. And if sometime in the future I will build networks where I can use these CAN-XL nodes as real CAN-XL nodes, then I will be able to reuse this piece of hardware, and that's the beauty of it. So it's a kind of downgraded CAN-XL node here. And it makes no difference if I put here a SIG transceiver under CAN-XL node or a SIG XL, they can work or operate in the same way here in this network. However, if my application runs with CAN-FD and I'm happy with it, I can still build a pure CAN-FD network with 5 megabit, no question about that. How can I do that? So we said, okay, we need better transceivers. So we, in all nodes, use SIG transceivers. And that means I can go for a higher arbitration phase bitrate. And I now can configure in the FD data phase 5 megabit. And yeah, the XL data bitrate is not configured. We don't care about it. And the nodes only can send CAN-FD frames, error signaling is on, and everything is fine. And this is how I can build a CAN-FD network with 5 megabit, a pure CAN-FD network. And finally, I have a last example. And this is an example where I started integrating also classical CAN nodes, so legacy nodes, take over parts maybe, since because when you build something new, you never develop everything new. You have always take over parts. And here you see, I need to downgrade my CAN-FD nodes to only talk classical CAN. This can be already also done by software, The CAN XL nodes are also downgraded to talk only classical CAN. And for sure, the classical CAN nodes just stay as they are. I have only 500 kilobit in this network. Error signaling must be enabled in the XL nodes, and it will work fine. So this means here I have a really downgraded ECU that only supports now classical CAN. And here you see the flexibility of the new CAN XL nodes. They can just be used everywhere. And we think this is a big benefit because flexibility is always very valuable. Okay, now I come to the summary, and I have 3 main messages for you. This was a lot of stuff, but I tried to bring it to the point to 3 messages. Message 1 is CAN XL and CAN FD are fully compatible when the CAN XL node has error signaling enabled. That means I'm limited to 5 to 8 megabits, and I can build such a network. And in this network, as we saw, the CAN XL and FD data bitrate can even be different if we want. Then the second message is that pure CAN XL networks provide the highest bitrates when CAN XL has error signaling disabled. So disabling error signaling enables us to use the new transceivers, and then we can do 12 megabit and even more, and we are limited to pure CAN XL nodes and pure CAN XL communication in this network. And finally, also an important message is CAN XL ECUs are usable in any CAN network, in a pure CAN XL network, in a mixed FD XL network, in a pure FD network, and in a pure high-speed CAN network. So I can use the CAN XL node, the CAN XL ECU, extremely flexible. Okay, so thank you very much for listening. This was what I wanted to show you. I hope you understand now the compatibility better between CAN XL, CAN FD, and also in combination with the transceivers. Maybe not all questions are answered, but now we have the questions and answer session. I think 10 minutes or 11 minutes are left, and I'm happy to answer your questions. Thank you very much.